data were collected for N2 plus 3H2 going to 2NH3 at a particular temperature. And the temperature is not specified. At a particular temperature. Okay, so here's what it looks like. Let's go ahead and do, yeah, that's fine. You know what, I'm actually going to start the data on another page. So the following data were collected for N2 plus 3H2 goes to 2NH3 at a particular temperature. And now I'll go ahead and give you the table. This is the experiment. This is the initial concentration, the equilibrium concentration, and the actual K, which we know the expression for. So we have 3 experiments. We have one experiment. The N2 concentration was 1.000, and of course concentration is in moles per liter. The H2 concentration is at 1.000, and the NH3 concentration was 0, and our equilibrium concentration, when we measured it, is 0.921, 0.763, and 0.157, and the K ends up, so this is, now the K is equal to NH3 concentration squared divided by the N2 concentration times the H2 concentration cubed. That's our equilibrium expression. The K ends up equaling 6.02 times 10 to the negative 2. When we did experiment 2, we found the following. We started with an N2 concentration, an H2 concentration, an NH3 concentration, and we did, this time we did 0, 0, and 1.000. I'll go over and discuss what all of this means in just a moment. And we ended up with 0.399, 1.197, 0.203. Okay, and when we calculated K, we get 6.02 times 10 to the negative 2. Notice they are the same even though these are not. And we did one more experiment, and we started off this time nitrogen, hydrogen, and ammonia. We did 2.00, we did 1.00, and 3.00. And we ended up with nope, we don't want these stray lines. We did 2.59. We did 2.77 and 1.82, and when we 6.02 times 10 to the negative 2. Okay, so here's what's going on. We did 3 experiments. The first experiment, what we did is we measured initial concentrations. So we put in a flask 1 mole per liter of nitrogen gas, 1 mole per liter of hydrogen gas, and no ammonia. We let the system come to equilibrium. We came back. Once it reached equilibrium, once we realized that these values are not changing, everything is constant, we measured them. Turns out the nitrogen concentration was 0.921, hydrogen concentration was 0.763, and the ammonia concentration was 0.157. We put these values, because they're equilibrium concentrations, into the equilibrium expression. Ammonia squared over nitrogen times hydrogen cubed. Let me rewrite the nitrogen to make it a little more clear here. We're dealing with N2. And what we did was got a number, 6.02 times 10 to the negative 2. That's fine. Equilibrium concentrations, we stick it into the expression, we get a certain number. Now, a whole different experiment. This time, the initial concentration of the nitrogen or hydrogen was 0. We just put in ammonia in the flask, and we let the system come to equilibrium. In other words, the ammonia started decomposing. Now nitrogen and hydrogen are forming. At equilibrium, when the concentrations were constant and nothing was changing anymore, we measured the concentrations. Well, now the nitrogen is 0.399, hydrogen is 1.197, 0.203. Completely different equilibrium conditions. Completely different. We started different. We ended at different concentrations. But notice, when we put these numbers into this expression, bam, 6.02 times 10 to the negative 2. The same number shows up. Interesting pattern. Experiment number 3. This time, we start with a little bit of everything. We start with 2 moles per liter of nitrogen, 1 mole per liter of hydrogen, 3 moles per liter of ammonia. Well, we let the system come to equilibrium. All the concentrations are now constant, no longer changing. We measure it, we get this, this, this. We put this into the equilibrium expression. What do you know? 6.02 times 10 to the negative 2. This is proof that these things right here, these are equilibrium conditions. Equilibrium conditions depend on the particular experiment that you're running at any given moment. These individual numbers are different among the experiments, but the relationship based on the equilibrium expression of the products raised to their coefficients, stoichiometric coefficients, divided by the reactants raised to their stoichiometric coefficients, that number stays constant. This is very profound. Anytime you have some data and data which should not have anything to do with each other, when you mix and match and when you keep getting the same number over and over again, you have something very, very special there. That's the whole idea. Much of science is based on trying to elucidate some sort of a constant. What stays? And this is what it is for the equilibrium condition. At this temperature, this reaction, this is a fingerprint of that reaction. Equilibrium does not change. Equilibrium conditions change. The equilibrium constant doesn't change. That's why we call it a constant. It is a fingerprint for that reaction. Okay. So, last but not least, let's distinguish between the equilibrium constant and the equilibrium position. These are equilibrium positions. That varies depending on the experiment. This is the equilibrium constant based on this expression. It does not change. It is not variable. So we speak about constants and we speak about conditions. Very, very simple. Very important. Okay, so hopefully this has given you a sense of what equilibrium is. Again, profoundly important topic. Those of you that go on into biology, biochemistry, biophysics, things like that, the equilibrium condition, or physics, any kind of science, all systems tend toward some kind of an equilibrium. It's the reason we're alive, because our bodies are constantly are trying to maintain a certain equilibrium. In fact, if you want to give sort of a broad definition of disease, a broad definition of disease is a deviation from equilibrium. That means something is going wrong. The body is trying to bring things back to equilibrium. Equilibrium is where everything wants to be, the point of lowest energy. And we can express that mathematically with chemical reactions with these expressions. It's actually quite amazing that it's this simple. Thank you for joining us here at Educator.com and for AP Chemistry.